Everyone, welcome back. Ever wondered if we can just keep making AI smarter by throwing more data and more computing power at it?
Interesting question.
That's what we're tackling today.
Okay.
We're diving deep into some research that really flips the script on how we think about building these powerful language models.
Yeah, it's fascinating stuff.
So we're not talking about some small tweak here. This research is fundamentally about scaling up the scale of these language models. What exactly do we mean by scale in this context?
Well, imagine building a brain, but instead of neurons, we have parameters. Think of them as connections that let the model process information.
Okay.
The more parameters, the bigger the model. But it's not just about size.
Right.
It's also about how much information we use to train it, the size of the data set, and the raw computing power we blast it with.
So it's like the difference between having a casual conversation and, like, devouring every book in the Library of Congress. The more you feed the model, the smarter it gets.
Exactly. And what's really cool that this research found is that within reason, the actual architecture of the model, the specific design, matters less than just going big on these three factors.
Wow, that's kind of mind-blowing. So a simple model trained on a massive data set with tons of computing power could potentially outperform a super complex model with less oomph behind it.
That's the gist, yes. It's like baking a cake. A more complex recipe doesn't always guarantee a tastier cake.
Right.
Sometimes the quality of your ingredients and the power of your oven have a bigger impact.
Okay, I'm starting to see why this research turned heads. But how much better are we talking here? Is there a way to predict how much a model will improve by just scaling things up?
That's where it gets really interesting. They found that this relationship between scale and performance follows a specific pattern, a power law.
Power law, okay. I vaguely remember this from high school physics, but remind me.
Think about earthquakes.
Oh,
A small increase in magnitude on the Richter scale can mean a huge jump in energy released.
right.
That's a power law in action. And the researchers found that these power laws apply to all three scaling factors in language models.
So if I double the size of my data set, I don't just get double the performance, I get like an exponentially bigger improvement.
You got it. And it's the same for model size and computing power. This power law relationship is what makes scaling so impactful. Double the resources, and you're not just incrementally improving, you're potentially making a giant leap forward.
Okay, this is all very exciting, but there's always a but, right?
Yeah.
It can't be as simple as just building bigger and bigger models. What's the catch?
You're right, there's a catch, and it comes in the form of a classic machine learning headache called overfitting. Imagine a language model trained only on sports articles. It might write amazing commentary,
Sure.
but struggle to summarize a scientific paper.
Okay.
That's overfitting.
So it's like that student who aces all the practice tests, but then freezes up on the real exam because they memorized the answers but didn't actually learn the material.
Exactly. In the world of language models, this means they become too specialized to the data they were trained on and don't generalize well to new, unseen text.
And that's a problem because we want our language models to be versatile, right? Like, I don't want a language model that can only write screenplays about talking cats, as fun as that might be.
Right. And this research actually discovered a way to predict and manage this overfitting problem, which is a huge deal.
Okay, tell me more, because this feels like a potential game changer. How do they tackle this overfitting beast?
They found that it boils down to the ratio between the model size and the data size. Think of it like building a skyscraper. You can't just keep adding floors without reinforcing the foundation.
So as you scale up the model, making it bigger, more complex, you also need to proportionally increase the amount of data you use to train it.
Yes, but here's the surprising part. It doesn't have to grow at the same rate. It's more like a balancing act. The researchers actually developed a formula.
A formula? Now that's getting really interesting.
Yes. This formula helps us understand how much we need to scale our data as we scale our model. It's like having a roadmap to avoid overfitting, which is incredible.
So no more language models that can only write limericks about squirrels. Thank goodness for small miracles. But seriously, this formula sounds like a powerful tool for developers.
Absolutely. And this is just the tip of the iceberg. This research uncovered even more insights into how to optimize the training process itself to make sure we're training smarter, not just harder.
Training smarter, not harder.
Right.
I like the sound of that.
Yeah.
But we're talking about training these massive language models, right?
Yeah.
The ones with more parameters than stars in the galaxy, or at least that's what it feels like sometimes.
Yeah.
That's got to take some serious computational muscle.
It absolutely does. It's like running a marathon, but instead of leg muscles, we're talking about computer processors working overtime. And just like a marathon runner needs the right strategy, not just brute force, training these models efficiently is crucial.
So how do we make sure these AI marathons don't turn into expensive flops?
Well, one of the key findings in this research is this concept of a critical batch size. Imagine you're baking a cake and you're trying to figure out the perfect oven temperature and baking time.
Okay,
You know,
I'm following.
there's a sweet spot that gives you the best results. Not too doughy, not too burnt.
Right.
Exactly. The critical batch size is like finding that sweet spot for language models. It refers to the optimal amount of data to feed the model at any given time during training.
So it's not just about cramming in all the data at once. It's about finding that Goldilocks zone, not too big, not too small, to optimize how quickly and efficiently the model learns.
Precisely. And what's fascinating is that this critical batch size isn't a fixed number. It actually scales along with the model's performance. As the model gets better at its job, as its loss decreases, the ideal batch size increases as well.
So you're constantly fine-tuning, adjusting the batch size as the model improves.
Yeah.
That's pretty cool.
It's a feedback loop.
Almost like a feedback loop.
Yeah.
But let's talk about something else that really caught my eye in this research. The idea that bigger models are inherently better learners. We intuitively get that bigger can be better, but what's the science behind that?
It's a bit like the difference between trying to learn a new language by studying a phrase book versus immersing yourself in a country where everyone speaks it.
Right.
The more data you're exposed to, the more effectively you learn, right? And larger models, with their massive parameter count, have a greater capacity to absorb and utilize information.
So they're like the ultimate language sponges, soaking up knowledge from every bit of data we throw at them.
That's a great way to put it. This concept is called sample efficiency. The researchers found that larger models can achieve the same level of performance with less training data compared to smaller models.
Which seems a bit counterintuitive at first. Why would we even bother with smaller models if larger ones are so much more efficient?
That's where those pesky real-world constraints come in again.
Yeah.
Building, and more importantly, training those massive models demands an incredible amount of computing power, which translates to time and money.
Right.
Yeah.
It's like saying, sure, I could learn a new language by, living on a private island and hiring 1,000 tutors, but
Right.
my budget says Duolingo it is.
Exactly. It's a
Yeah.
trade-off.
Yeah.
This research gives us a framework to make more informed decisions about those trade-offs.
Right.
If you have unlimited resources, then by all means go big.
Sure.
But in the real world, knowing how to optimize model size based on available resources is incredibly valuable.
So it's like investing in a high-quality tool that might cost more upfront, but ultimately saves you time and resources in the long run.
Yeah.
But speaking of limits, all this talk of bigger is better makes me wonder, is there a ceiling somewhere? Can we just keep scaling up these language models indefinitely?
That's a question that even the researchers grapple with. While the possibilities seem endless right now, even language itself has a finite amount of information you can extract from it.
So even if we created a language model the size of, I don't know, the entire internet, there's a point where it hits a wall and can't really learn anything new.
Yeah.
That's both fascinating and a little bit unsettling. It does make you think, like trying to squeeze water from a rock. Eventually you hit a point where there's just nothing left. But are we really approaching that point with AI and language?
It's a possibility the researchers didn't shy away from. They even tried to put a number on it, estimating this potential limit might be reached with a model containing something like 10 to the power of 12 parameters.
Okay, for those of us who don't speak exponent, how massive are we talking here?
Imagine a language model with trillions upon trillions of those brain cell connections we talked about. It's a number that's almost impossible to wrap your head around.
That's just mind-boggling. And a little terrifying, to be honest. But it also sparks so many questions. What happens when or if AI reaches that point? Does it just plateau? Or does it force us to rethink how we approach artificial intelligence altogether?
That's the million-dollar question, isn't it? It could push us to explore entirely new approaches to AI, moving beyond language as the primary input. Maybe we start looking at integrating sensory data, emotions, even subjective experiences, things that are much harder to quantify, but are fundamentally human.
So instead of just teaching AI to read every book ever written, we start teaching it to understand the world the way we do.
Yeah.
Through sight, sound, touch, all of it.
Exactly. Or maybe this potential limit forces us to confront the limitations of our current understanding of intelligence itself. What if there are entirely different ways of processing information and generating knowledge that we haven't even begun to imagine?
Well, this is quickly moving into the realm of science fiction, but it's exciting to think that this research, while groundbreaking in its own right, could be just the tip of the iceberg. Maybe we're not approaching a limit, but a doorway to a whole new understanding of AI and its possibilities.
Absolutely. And as we venture further into this uncharted territory, one thing's for sure. The discoveries we make will continue to challenge our assumptions and redefine what's possible.
Well, there you have it, folks. We've explored the incredible potential of scaling language models, uncovered the power of power laws, how fitting, and even grappled with the mind-bending implications of reaching the limits of language itself. Who knew a single research paper could spark so many questions?
It's been a pleasure diving into these fascinating concepts with you today. Remember, the quest for knowledge is never truly over. Keep those questions coming, and never stop exploring the ever-evolving world of artificial intelligence.
Until next time, stay curious.